Okay, so hello everyone. I'm Marius. So I will talk about the latest results for the CAST-CAPP detector on behalf of the CAST collaboration. So let me start. A very brief overview. Basically, you know all this stuff already. So just maybe for some of our WIMPs friends. So Axions, actually we have two big problems in particle physics and cosmology, the strong CP problem and the dark matter problem. For the strong CP problem, we have this, where is the laser pointer? Here. So we have this theta parameter, which is appears in the QCD Lagrangian and is very, very small based on experimental observations. And we also have a dark matter problem where we have much more mass in the galaxies than expected. So the common solution many, many years ago by Peche and Quinn that they introduced a new symmetry where they showed that after spontaneous breaking of this symmetry, we have a new Goldstone boson, the axion. And this has some very nice properties. It has no electrical charge, it has a very small mass, and it is very weakly interacting, which actually, based on its mass and its density in the universe, it makes it an ideal candidate also for dark matter. And, but this is the theory how you are supposed to detect this. So it has a specific property, except from its coupling to nucleons and electrons. The axion can also couple to two photons. So if you put the axion in a strong magnetic field, then it converts into a real photon. And this is something you can detect. And this is also what most experiments are using for this detection. For the microelectron volt case, we have the so-called axion haloscope technique, which is the most prominent one to search for the axion. So this involves high-quality microwave cavities, which are immersed in strong magnetic fields. And if the outgoing photon from the axion conversion is found inside a cavity which resonates basically to a frequency of the corresponding to the axion mass, then the enhancement rate is further enhanced. So for rectangular cavities, it's convenient to have here the magnetic field perpendicular to the lateral sides. And you see here that the mode frequency depends basically on the cavity dimensions. So this means that if we want to go to higher frequency, to higher axion masses, then we must build smaller cavities. And this is a problem, as actually I think Ben Felix mentioned yesterday, that high frequency is difficult. And this is, he had the point, except of all the mechanical stuff. The volume also decreases, which means that the axion signal power also decreases as well. So you see that from the signal-to-noise ratio, here is the decay radiometer equation. So it depends on the axion signal power and the uncertainty in the noise. So all experiments actually try to increase the axion signal power while minimize the noise system temperature. So we go to CAST. You have basically seen CAST in throughout all these years in several presentations. You see it in mostly in all plots of the exclusions. So CAST has been running for many years as an axion helioscope. Actually, more than 20 years it was running as an axion helioscope and searching for solar axions. And then in 2019, we succeeded to convert it into an axion haloscope as well, searching for dark matter axions. So you can see here how CAST looks like. Probably you know this already. We had the two more detectors, the micromegas detector looking for solar axions and the K-WISP detector looking for chameleons from the dark energy. And the dark matter axion detectors, we had CAST-RADES and CAST-CAPP, which I will show you here. So the CAST-CAPP cavities. I said before that when you are going to higher frequencies, you unexpectedly have to have smaller volume. And when you have smaller volume, you have to decrease the axion signal power. So in order to mitigate this issue, we have used not one cavity here, but 4 identical cavities, which were inserted one after the other inside one of the 2 bores of the CAST magnet. So you can see here some characteristic numbers of the cavities. We had a load quality factor of around 20,000 and a noise temperature of less than 10K. So you can see also how the cavity looks like. You have several elements. You have a piezo actuator that I will show you later. You have tended sensors, couplers, amplifiers, and a locking device to keep it in place inside the magnet board that you see here. So this is a picture of the magnet board. You see how small it is and how difficult it is to put all this inside. So the first thing was to use 4 cavities that I told you. With 4 cavities, though, the signal-to-noise ratio increases with the square root of n, so in our case, factor 2. But you can actually use another technique which is known for many years in antenna theory. This is called the phase matching technique, which as far as we know it was used here for the very first time in Axion dark matter research. So with this technique, what you basically have to do is combine coherently the power outputs of each cavity. And if this is done properly, if you do for example, here the combination after the individual amplification, then the phase matching increase in the signal-to-noise ratio accounts for a linear increase in the SNR. So in our case, you have a factor 4 increase of the SNR. But how you can do this? In order to do this, you need basically 3 different factors. You need to frequency align the cavities at the same frequency within a tolerance, which here you can see were much, much better. You need to align the amplitudes of the resonance peaks as well. This was done by programmable attenuators, and you also have to match the phases of the sound waves in case there is an action signal. So you basically have to adjust the electrical outputs, the electrical delays of the outputs of the various cables, and this was done also here as well. And when this is done correctly, as I said, you basically have this increase in the signal-to-noise ratio. This feature actually is very important also for future large-scale haloscopes. So this is important to keep. Now the action mass is unknown. This is a problem, so we have to have basically a tuning mechanism in order to be able to scan in a region of space, of a parameter space. In CAST-CAPP, we do this with this novel mechanism that I show you here. So we have 2 sapphire plates which are installed inside the cavities, and they are activated by this piezo motor that I showed you before. So, as we will see also later in our results, this allows for a scanning of about 660 megahertz throughout the parameter space. But CAST-CAPP does also more than conventional dark matter actions. So, together with conventional dark matter actions, we can also scan for other events, for other streaming events, transit like streams or mini clusters. And as you saw probably before by Konstantin or yesterday by Abbas, the various talks please go through. So we can have basically gravitational focusing by the planets and the sun, or self-focusing by the Earth itself, which leads to a significant flux enhancement. And this is important. So in order to take advantage of these various events, you must have 4 different options. First of all, since you don't know basically the velocity profile and when these events happen, you must have a fast scanning technique in order to be able to take advantage of these short-lasting bursts. So this is why we have, I showed you before the tuning speed. Usual experiments don't show this, and for our case, it's about 10 megahertz per minute, because the faster the speed you have, the shorter the burst that you can probe. Then also, your detector should have a wideband electronics and a fast daily, in our case, analysis and elimination procedures, so that you can go back to the frequency and recheck if there was a transient event or something else. Of course, since you don't know the exact date and time of these events taking place, you must also have a duty cycle as big as possible in order to probe for these events. So this is an overview of our DAC system. So it's only about 40 instruments outside of the cryostat. So we take like 1 minute measurements, and we have a tuning step size of 200 kilohertz, which is defined basically by our quality factor. And as I told you before, we will see later on, we have daily analysis and processing procedures. And let me move to the next, to our results. So these are some of our first results. We have taken data for 172 days in total throughout these 2-3 runs from 2019. And we also have successfully done phase matching in data taking conditions for all 4 cavities. We used also the fast resonance scanning technique, and then therefore we managed to probe an unexplored parameter space. We also had to do some quality checks in our data that we take in order to make them free from unwanted effects, such as mechanical vibrations, which are unfortunately we could not avoid in such environments as CAST, which is noisy. So we applied some quality checks in our data, and we have excluded basically 4.4% of our data based on these effects. Then we record our data in the raw time domain. So afterwards, we have to apply an FFT in the processing procedure to transform them into the frequency domain using a resolution bandwidth of 50 Hz. Of course, we can then go back and redo it. in a smaller resolution bandwidth. So the data analysis is basically the same as most experiments which are presented here are doing. It basically consists of five steps. The very first step is a spectrum flattening, where you have to apply a smoothing filter. In this case, we apply the Savicii-Golay filter in order to remove the noise baseline. You see how the spectrum becomes afterwards. The second step was to check for IF parasites. In our case, you can see here that we have two. These are independent of the frequency of the cavity, so they appear in the same fixed index regardless of the cavity frequency. And then we have to combine the various spectra that we take. In this combination, we have basically three sub-steps. First, we have to scale the spectra to get the correct axion SNR. Then we have to combine the spectra by vertical averaging on the RF axis. For this, we use the maximum likelihood principle. And then we have to normalize to have a normal distribution of mu equals 0 and sigma equal 1. Then we take this combined spectrum and we aim to increase the SNR of an axion signal based on the expected dark matter axion line width of 5 to 7 kilohertz, which if this is deposited here in 5 bins, we have to average the various spectra in 28 adjacent bins. So the resolution bandwidth of the bin spectrum becomes 1.4 kilohertz from 50 hertz that was before. And finally, the last step was basically to create the grand spectrum by convoluting with expected Maxwellian, basically, axion line shape. So we have to make sure as well that the analysis procedure that I mentioned is working properly. And in order to do this, we have to introduce some fake signals. So here we injected hardware-wise and software-wise some fake signals. So you can see that by time evolution, the signal appears as it's supposed to be. And also software-wise, after you apply the previous analysis steps, you can see the correct action, frequency and coupling of the axion that we injected. So these signals are something that we wanted. There are also signals that we didn't want. So in this kind of experiment, there are ambient signals from parasites outside. So no matter how good your shielding is, in our case, we have the body of CAST as a Faraday cage, but there are also signals, parasites coming in from outside connections and feed-throughs and cables. So the good point was what we had a noise level, so signals below this noise would not be inserted inside, but signals above they would. So we had to take 2 steps basically to mitigate this issue. The first step, I will start with solution B here, is to basically deactivate any intervening things emitting in the area like the W line. So you can see here how the spectrum looked like before and after the disabling. And then the second solution was to introduce a second measuring channel, a second spectrum analyzer connected to an external antenna, which was outside the cryostat, looking for this simultaneously for these signals. So if we have a signal at the same time inside the cavity and in the external antenna, this would mean that this was a parasite and is discarded from further consideration. So we did our analysis. So we set our target SNR to 5 sigma and our confidence level to 90%, which leads to a threshold of 3.72 sigma. This is this red line here. So we scanned the grand spectrum and we saw 60 outliers. But of course, we had to follow our predefined elimination procedure. So basically, we had 11 of them verified as blind signal injections. Then 9 of them were verified with the previous thing that I mentioned before as parasites from the room. And then we had to rescan these false positive basically outliers, which actually disappeared after following these steps. So the grand spectrum after this procedure unfortunately didn't show any line above a threshold. So I go to the results. So these are the latest exclusion plots. So we managed to scan axion masses from 19.74 to 22.47 microelectrovolts, and we reached a sensitivity of up to 8 times the KSVZ theoretical line. So you can see also here on the right side how our exclusion plot looks like comparing with the other experiments in this region. So I go to the last slide, to the summary. So we have scanned the previously unexplored parameter space, and these are the novelties that we have introduced. We used for the very first time here a dipole magnet, a decommissioned dipole magnet CAST, as a dark matter axion haloscope. We had no mode crossings actually using this setup over the entire tuning range for our mode of interest. And then we used 4 identical cavities coherently combined with this phase matching, novel phase matching technique to increase the SNR. We introduced a state-of-the-art tuning mechanism of resulting to a wide mass range of 660 megahertz. And of course, we use this novel fast scanning technique that I told you to be able to probe also for transient events and scan basically faster also outliers. Then we introduced a second measuring channel for parasites. And we started designing a new approach and a new analysis techniques for this kind of transient events, also for the time domain option, to search for such signal modulations. And you can see here, for example, how the prospects, if you want to reach, for example, with this setup, the theoretical band with conventional halo actions and with streaming actions. So this involves a minimal flux enhancement of 10 to the 2. And you can see that it is a matter of hours, not days. And this is a minimal, I said, because also Abbas mentioned yesterday much higher numbers. So that's all. We just have to be patient. Maybe the action is just around the corner. And so you have to still keep looking for it. Thank you very much.
Hi, Marius. Very nice result. Thank you. Congratulations. So I have a question about the detecting the transient event using single experiment. I'm not sure whether it is possible unless you have like a global net or something like that, because transient event is not going to be reproducible. So it's really hard to verify that the signals is from the transient event.
Okay, so because I didn't hear you very well, you mentioned that the transient signals, right? So yeah, in principle, if you want to verify it unambiguously, you need to use more than one experiment, preferably located in different locations due to verification checks. So unambiguously, to make a verification of this, yes, this is true what you say, that you would need simultaneous experiments working at the same frequency. So yes, this is true. But of course, if you see something, this is an important hint, because if you see, for example, a transient signal that you were not expecting, then you can go through and scrutinize it, and then you can go back and recheck it with the same or other experiments at this frequency. So this would be a very nice, very first hint on that there is something there which shouldn't be.
Correct.
But in reality, what you say is correct.
Right. Thanks.